thank you so much for the introduction. And I hate to be the guy that's between you all and beers later, but I am that guy today, so bear with me. So today I'm going to be talking about DuckDB. But first, I'd like to start off, who am I, right? Like, why am I here talking to you guys about database systems? So I did my PhD in database architectures at CWI in Amsterdam as like one of the biggest research groups related to database systems. And I mainly did my PhD in index structures, which is of course the reason that the first thing I did in DuckDB was an index structure. It all makes sense, you know? I'm currently a COO and software developer of DuckDB Labs, which is the company we have to support the open source project of DuckDB. And as you guys can see in this picture, so we kind of start coding DuckDB in July of 2018. I was right there, so that's like my gamer tag that became my developer tag later on, with Mark and Hannes early on. And I did like all kinds of stuff in DuckDB, you know, like I implemented indexes, zone maps, Arrow, ADBC, substrate integration, a lot of the Python API. So if anyone uses DuckDB in the Python API and it breaks, there's a big chance it's me, so you can email me with some bad words. CSV reading, bunch of other stuff. I've been all around the place there. And this talk, we're basically going to start with some motivation. So what's an in-process database management system? What are the alternatives to in-process database management systems? Then we're going to go through DuckDB, what is DuckDB, designs, what the API looks like, a short demo, and the summary of the talk. So motivation. So in-process database management systems, right? Like, what are they actually for? And if you think about it, they're mostly used for data science, so in combination with analytical tools for Python and R. And why is that? The thing is, in-process database management system can actually run in the same process as analytical tools. So the memory you have from your analytical tool and your database management system is the same, which means they can both access the same data without copying it. So this completely eliminates one of the biggest problems of doing data science or interactive data analysis, which is copying and transferring data. So they're also very used in data visualization and reporting tools, in IoT and sensor data, BI and analytical tools, and exactly because they can do this fast data transfer, due to zero copy, and they do resource sharing, right? Because since they're the same process, they are also sharing the resources of the machine with the application tools. So you can do some clever things with sharing memory or processing power, for example. So to give you an idea of what kind of like this data science problem looks like, right? So data science is usually very exploratory, interactive, trial and error, hypothesis driven. So what do I mean by that? Usually you have data sets and you come up with a hypothesis. And then you start querying your data sets to either justify, okay, my hypothesis is correct, or oh no, I'm completely wrong, I'm going to zoom out from this part of my data sets and start zooming in somewhere else. So usually you have this type of workflow, right? Like you ask an interesting question, you get the data, you explore it, you model with some magic AI, you do some visualization, and you repeat. And when you think about what kind of tools we usually have in each part of this workflow, is that when you're asking interesting questions and where you're exploring the data, you basically have a database management system, right? Or a data frame library. So you're basically issuing queries and getting results. The data, of course, comes in all shapes and forms. So we have JSON, CSV files, Parquet files, binary files, because they were already stored in the other database files. To model the data, you can think of things like PyTorch, TensorFlow. And to visualize it, there's also many libraries like Plotly, Tableau, or whatnot. So if you're not going to use any database, in-process database management system, what could you use, right? And what are the like necessary things that you need for this type of workflow? So what are the important things? One of the things that I just showed you is that data comes in all shapes and forms, so whatever you're using, whatever tool, needs to be able to scan all these different file formats, right? Because you're plotting and because you're doing these machine learning interactions, you also need to integrate with this ecosystem quite well. And with integration, it means that you need to communicate with them, preferably without copying data. You also want to be a very efficient analytical execution engine, because as I showed you guys before, there's these two steps where you're basically just querying your data constantly. So you want to do things like beyond memory execution. You don't want that just because your data cannot fit in memory, your Python application crashes, for example. And you want to be able to do complex query optimization. So you want to be able to push down your filters, push down your predicates, to do join ordering, all this cool stuff. And of course, okay, I'm completely biased because I love database systems, so I love SQL. This is the way, by the way, to query data. But I know a lot of programmers love this kind of relational API, more data frame-ish. So you need to be able to support both, just because there's these two different crowds that are doing data science, data analytics, and they use each one of those. And most important, it needs to be something that's easy to use. Data scientists, programmers are not really that willing to spend like a day just installing a database management server, starting the server, creating schemas, loading the data. It must be like, bam, you can just do it. So if you think about traditional relational database management systems, right, like PostgreSQL Server, Oracle, they're great. Has like 50 years of database research embedded in them. They have amazing query optimizers. They do buffer management, which means that you can query data that's over your memory. They have their own storage. They probably have compression in their storage. They have amazing execution engines, also based focused on analytical queries, and they have full SQL. However, of course there was a however, they are horrible to set up. If anyone here has tried to set up a database server and knows you cannot do that in 30 seconds, right? Like, it's going to take you a while. And if you've never done it before, it can even take you days. They require upfront schema creation. So you need to know exactly what the data you're accessing looks like. What are the types, what are the column names. They lack integration with the analytical ecosystem, and you can see here. So you have your relational database, you have your Python application. All your data is going through this guy. Database connector, and turns out this is not efficient. This becomes a huge bottleneck when you're trying to do data analysis. And because of that, they suffer from huge transfer costs. So not a great idea. And actually, I have a very personal story about this. When I was doing my PhD, my project was paid by a company that was doing a lot of data science, like many data science pipelines. And I got there and like, oh, these people are probably like all over databases, right? Like, it's going to be amazing. And I go there, and they hated database systems. They were all using pandas, and that really surprised me. And why did that surprise, right? Pandas are data frame libraries. Everyone loves them. Everyone uses them. They really integrate with these ecosystems. That's the reason they use it. So you can talk NumPy, you can talk PyArrow, but the main reason is because they're easy to use. Everyone that uses pandas knows you can read a CSV file with 2 lines, right? Import pandas, pandas read CSV, bam, done. They do the relational API. Sometimes people don't want to do SQL. They want to do their data frame-ish language. I respect that. That's okay. So it's all there. They have the fast data transfer because, again, these libraries, they are embedded in the Python process. So when they have to communicate with these other tools, like TensorFlow or PyTorch, PyTorch talks NumPy. Pandas talks NumPy. There's no cost. It's just great. And they have integrated scanners with automatic schema detection to multiple file formats. If you do the pd.read CSV with your CSV path, Pandas infers everything. You don't need to pass delimiters. You don't need to say if there's a header. Like, it's just good. It feels good to use, right? So what's the problem? Well, the problem is that they don't have the 40 years of database research that database management systems have. So query optimization, Pandas doesn't even do the basics of query optimization, which are like projection and filter pushdown, for example. They don't support SQL, completely away. They just won't support it. Beyond memory execution, if anyone here tried to use Pandas on data that doesn't fit in memory, the whole machine goes to fire, right? Just crashes. I think no one likes to see their Python application crashing, right? It kind of feels bad. They have lack of storage, so you're kind of limited to just handle your CSV, Parquet files, and whatnot. You're not going to do anything smart about it because you can't. And they have very limited parallelism. Doesn't matter if your machine has 4 cores, 8 cores. Only one will be used. So that seems a bit wasteful. And that's how we came up with the idea of DuckDB. It's like, can we actually get everything we've been studying about database research and the nice things about data frame libraries, like this feels good to use, combine them and make something new? And we actually drew inspiration from the most used database system. I guess some of you might have never heard about it, but it's SQLite. SQLite is an embedded database system, so he has all these cool things of no external server management, it's pretty easy to use, bind to every language, so it doesn't really matter if you're doing R, Python, name a programming language, it has bindings to it. The database is stored in one single file, so if you have 15 CSV files, you can transform it to one SQLite file and send it over easier. Public domain, and it's the most used RDBMS. So this thing runs on everything. It runs on all of your cell phones, it runs on airplanes, it runs on every single browser, everywhere. So like, can we actually get SQLite and make it work for analytics? Because that's the thing, right? SQLite is amazing, but the whole concept is that it's very fast for transactions. So we wanted to do that for data analysis. Then that's how DuckDB was born. It's our in-process OLAP, so for analytics, database management system. We kind of call it the SQLite for analytics. It's free, open source, under the most permissive license, which is MIT. And everyone is welcome to try it out after the talk, of course. And again, simple installation. If you want to start using DuckDB, you just do a pip install. It's embedded, no server management. Fast analytical processing, you have this very fast data transfer between our Python and the system. We support SQL as much as Postgres does, for example. Single file formats. We're currently in pre-release. We're actually on 0.7, we're going to be on 0.8 next week. There was a little bit of delay, but we're getting there. So my slides are from the future already. And this is, of course, like just to get this out, like, why is it called DuckDB? Because I always get this question, so this is not the question that I'm going to get today. If someone already sent it through the Google Docs, I'm sorry, but I'm going to answer it now. The reason is because ducks are versatile. They can fly, they can walk, they can swim. They sit on top of the data lake. No, I'm joking. This is a corporate answer. So the real reason is because Hannes, which is, by the way, one of the co-founders of DuckDB, used to have a pet duck. And that's a picture of Hannes and Wilbur, his pet duck. And he also lives on a boat, so I was like, I cannot really have a dog. I'm going to settle for the duck. And he was very fond of his duck, so he was very insistent on us naming it DuckDB, and we actually really liked it because there's this whole tradition of database systems being named as animals. So that's the real reason. All right, so let's go a little bit about with a crash course of database systems. I'm going to talk about the design decisions of DuckDB and why it makes it very special and very fast for data analysis. So we're going to talk a little bit about the data layouts, data compression, the type of execution engine we use, query optimization, parallelism, beyond memory execution. Sounds a lot, but I'm just going to scratch the surface. It's not going to be like an Andrew Pavlo lecture where I'm going to go into a lot of detail. If you actually want to see a lot of these things in more detail, you should check his course. So all right, so SQLite, for example, the data layout is a row storage. It means that the rows can be fetched very cheaply. However, every time that you fetch your data, you must fetch all the columns. And the reason for that is because your data is actually stored like this in memory. It's contiguously by row. So what happens if you just are interested in a few columns? So on this table here, for example, we have dates, store, products, customer price. But let's say you just want to know the price of a product, but not really the stores in which it's sold. In practice, that means that you're going to read the whole data there, because you cannot really skip it that easily. So you're going to read the first row, second row, third row, fourth row, so on and so forth. Doesn't matter which columns you're accessing. On a column store, that's already different, because we can actually fetch columns individually. And the reason for that is because the data in memory or on disk is not stored like this anymore, but is actually stored per columns. So this actually causes immense savings in disk I/O and memory bandwidth when you're just accessing a few columns. So again, if you have the same query as before that you just want one column, you suddenly don't read your total table anymore, but just that one column. And turns out that this is very common in analytical queries. Usually you have very wide tables, many, many columns, but you're really interested in a handful of them. So to give you like an idea of what that means in time, right? Because, okay, few columns, all columns, what does that mean? So let's say we have a 1 terabytes table with 100 columns. And for simplicity, let's just say they all have the same size, right? Like they're all integers or whatever, no strings here. And let's say we have a query that just needs 5 columns of this table, right? So in the row store, we're going to have to read everything from disk. No escaping that. Which means that 100 megabytes per second of throughput, that takes you 3 hours. On the column store, you're actually going to be able to read the partitions you need to share the columns. So 5 columns, goes 50 gigabytes, same speeds, about 8 minutes. So just this difference in layouts have significant gains. So any system that does analytics today, and you can think of the SQL Server version for analytics, you can think of pandas, they're all doing columnar storage. There's no way that you can do the other one because the gains are so huge. And the nice thing of column storage is because usually when you're storing individual columns sequentially, you have this benefit that they tend to have similar values, right? So for example, when you're storing dates, turns out that dates are usually in an increasing order. And that's quite cool because it allows you to apply compression algorithms that will reduce this throughput, that will reduce the cost of accessing this data even further. So here I have an example of the compression algorithms that were implemented in DuckDB. So you can see that in July of 2021, we had nothing. So no compression or storage. And at the end of last year, we had like 1, 2, 3, 4, 5, 6, 7 different compression techniques. I'm not going to go over them, but we do compression on floating point numbers, strings, integers. We really try to squeeze as much as we can. And we can see the ratios we got, right? So we have, for example, here the taxi data sets, commonly used in this data science benchmark, so maybe some of you know. And you have the line item from the TPC8s, which is one of the most famous benchmarking for analytics. And we can see that we managed to get like 5 times 4-line item in compression in a year and a half, and about 3.18 in the taxi data sets at the same time, just by applying these techniques. And again, what does that mean in time, right? Like, okay, 5 times, what does that mean? Is that if we get the same example as before, that we're reading 5 columns, 50 gigabytes from disk, and was taking 8 minutes, now this 50 gigabytes will become 10 gigabytes because it's compressed. So you're suddenly not taking 8 minutes to read your data anymore, you're taking 1 minute and 40 seconds. Execution. So SQLite uses this tuple at a time processing, which means that when you have your query plan, you're processing 1 row at a time. Pandas uses a column at a time processing, which means that you process the whole chunk of your column at every node in your query plan. And DuckDB is vectorized processing, which means that it processes batches of the column at a time. To give a more clear idea of what I mean by this, is that if we go to our example here, we have our table, and in our query process, that basically means that 1 line will be completely executed in our plan up to get the results. Then you have the second line, and so on and so forth. And this is actually pretty nice when you have when you don't have a lot of memory, because that actually means you only need to keep that 1 tuple in memory per time. So this model was actually optimized for when we didn't have a lot of memory in our computers, so that's why this was frequent in systems that are a bit older, like SQLites. But the problem with only keeping this 1 tuple is that you cannot cache your data on your CPU. So you have a high CPU overhead per tuple, and over time this becomes a bottleneck. The column at a time is kind of the opposite of the row. So again, you're just going to take the columns you're going to use. At every node of your plan, you're going to execute them fully until you get the results. And that actually has significant better CPU utilization. It uses the cache way better. It allows for SIMD, so you can do 1 instruction in a bigger chunk of your data. It has the problem that you start materializing large intermediates in memory. So if you have to execute 1 whole column or 2 whole columns on your, that means they need to be in memory. And that's one of the reasons that pandas just crashes when you try to read data over memory, because it needs to be there. So it becomes very problematic when you have larger data sizes. And the vectorized processing is kind of like the best of the two. So the idea is that you're not going to be sending a tuple, but like small chunks of your data. So it's really optimized for the CPU cache locality. It allows for SIMD instructions because you have batches of your data, pipelining, and the idea is that you have these chunks that are very small, so ideally they fit in L1. So here in the example again, we have the table. The table is going to query just like a chunk of our data, and then goes through results, then it gets the next chunk, then it goes through the results until we finish the execution. And just to clarify why this CPU cache locality is more intermediate mean, I'm not sure how many of you guys are familiar with how modern a CPU looks. But usually you have a core, and you have kind of like these caches, which are very small memories. And the thing is, the smaller it is, the closer it is to the core, faster it is to access. So you can see, for example, the L1 is 32 kilobytes. Oh, my keynote's actually hiding the times. But it's like 32 kilobytes, but it's 1 nanosecond. L2 is 256 kilobytes, and it's about 10 nanoseconds to access the data. L3 is about 20 megabytes, 20 nanoseconds. And the main memory can be, like, nowadays, I guess, almost anything, but has a higher latency, right? Compared to the first one, this would be like 2 orders of magnitude difference. And when your data is fitting in L1, so you have like these chunks that are always in L1, it means you're always paying the sweet price of 1 nanosecond latency to access your data. But if you think back on the column store, where you have a whole column, probably gigabytes, it's not going to fit in L1, it's not going to fit in L2, it's not going to fit in L3, it's going to fit here. So you're always going to be paying this latency when you're accessing it. Constantly, 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 this becomes one of the main bottlenecks in data analysis. End-to-end query optimization. So, of course, in DuckDB, we do things like expression rewriting, join ordering, subquery flattening, filter and projection pushdown. With filter and projection pushdown being like the basic one. Like that's what I would expect any system that does queries to do. So to exemplify to you what that means, let's say we have this table here with these 5 columns, A, B, C, D, E. Oh my God, this is really small. And we have a query that does a select minimum on A, where A bigger than 0 and groups by B, right? So what this means is we're doing a filter on A, and we're only really reading the columns A and B. So in DuckDB, what this will happen is that when we're scanning the data, the table, we're going to project only these 2 columns, which means we're really reading only them. And we're going to apply the filter in A when you're reading it. So we're not passing all this data to the other parts of the query. But if we do the same in pandas, let's say that we create this data frame called filter data frame, and we apply the filter first, we're applying the filter to the whole data sets. So we need to do these optimizations by hand. Pandas, for example, cannot do them for us. And then when we get to things that are really expensive as well, if you're not doing it correctly, but very hard to optimize, like subquery flattening, this is a no-go. So these things in the end make a huge difference. Automatic parallelism, so DuckDB has parallel versions of most of its operators, so you can think about scanners with insertion, order, preservation, so it means that even if you're reading your data in parallel, the order, whatever was inserted will be preserved, aggregations, joins, and just to give you an idea of what parallelism usually looks like, here we have time, here we have threads. It says memory limit here, but ignore it, it's supposed to be threads. The higher the threads, basically the cost starts going down. It's not exactly linear, but you get benefits from doing parallelism, from really utilizing all your cores. And we also do beyond memory execution. Basically beyond memory execution means if your data doesn't fit in memory, you're not going to crash. You're going to finish that query. So it's kind of, we have this motto, never give up, never surrender. Might take a while, but we're going to execute your query. And preferably with graceful degradation, right? So it's not because your data suddenly doesn't fit in memory that you're going to have terrible performance. You're going to have a little bit of worse performance, but it's not going to be horrible. So here in this example, I have a hash join. You can see here that I have the memory limits, so I'm decreasing the memory limits for my application. And you can see even when I decrease from 10 gigabytes to 1 gigabyte, so there's like a lot of buffering going on, goes from 2 seconds to 4, so it has a 2x. So you have an impact in performance, you will have, but you will finish your query, your computer will not catch on fire. All right, demo time. My favorite part, if it goes correctly. If it doesn't, I'll just cry a little bit. So this is a collab. Nowadays, collab actually comes with DuckDB by default, so I had to uninstall it because I want to show you guys something. But here in this first, actually, is it good for the people in the back? Can someone on the back? Okay, cool. So you can see here that I'm uninstalling it, but then I'm installing DuckDB, Polars, and PySpark, which are the things we're going to be, DuckDB and PySpark are some of the things we're going to be comparing today. And then I'm downloading 3 different data sets. So I have the famous New York City data sets from January of 2016, so just cab rides. I have a weather CSV file, and I have, I think this is a movies JSON, I don't remember anymore. It's been a time since I created it. But the first thing we can see here, so this is just like installing things and downloading them, right? So the first thing we can see is that here we downloaded DuckDB. This is the size of the binary, right? 15 megabytes. This is good. This is something you can download and run through Python. It's going to be fine. We see Polars, which for those that don't know, Polars is kind of like Pandas plus. So it has some improvements in performance. It's already a little bit bigger. And then you see PySpark. Do people here like Spark? Is there anyone very passionate about it? Okay, so please don't stab me on the exit. I'm going to be a bit mean to Spark today. So Spark, if you see the size, where is it? Here. 310 megabytes for a Python library. So it's quite big. So I'm expecting it's about 20 times bigger, 20 times better performance than DuckDB. That's my goal for today. If it's not that, I'm going to be like, I'll be annoyed. So let me just show you a little bit what DuckDB does in Python lands. So here's just a very simple example. We're just importing DuckDB and executing simple SQL and printing it out, right? So it's just like 42, int 32, perfect. We can also do everything from these flat files, and again, there's this feel good that I don't really have to do anything about it, right? So I just call the CSV auto function from DuckDB. I pass a path for the CSV. Bam, detects the header, detects the names, detects the types. I really have to do nothing. And I can read other kinds of things as well. I can do a parquet file. Same thing. I didn't have to do anything besides showing the path. I can do a JSON file. Same thing. Oh yeah, are these movies, right? Yeah. So in this case, it's just a small movie list. So the point here is that you can really do these things rather easily. In the second part, we're just going to create a little database for DuckDB, and we're going to load all these files into actual tables. And you can see one of the things that I like about DuckDB is that we have progress bars. So I kind of know when this is going to finish. There's no surprises. But this basically is going through the file and actually ingesting it into the DuckDB's formats. And then we can see a little bit about the DuckDB's API, right? So, we can actually see that DuckDB not only can read these files, but can also output them. So here we're just connecting to our database, and we are now getting a relation from the CSV table that we created up there, and we're getting a relation from the Parquet table that we created, and we're just creating these files again. So that's the whole preoccupation that we're constantly, that we can always read and write these things. And the same goes with very tight integration with the whole ecosystem, which I'll show you in a bit, for example, how we communicate with Pandas. So here I'm going to do some performance comparison. It's going to be between Pandas, DuckDB, and PySpark. So here I'm just importing the libraries. Here I'm just creating a relation over the the Parquet file we had with the New York City data sets, printing it out. So it's just like vendor ID, time, pickup dates time, drop-off dates time, so information about cab rides, right? And I'm doing accounts, so we have about 11 million tuples on this data set, so not huge, but sizable. And here, of course, coming from academia, benchmarking, you have to run it a couple times. So here I run the function 5 times. I get the mean value, not the average. I'm a good guy, I promise. So this is just to calculate the time and trying to be fair. And just to show you how we integrate with these platforms, I'm not going to be reading the Parquet file in DuckDB. I'm actually going to get a data frame from Pandas, because Pandas can also read Parquet files. And I'm going to be reading and benchmarking us executing queries in Pandas, and not in DuckDB directly. So the way this works in DuckDB is that I have, for example, this query. I'm selecting the passenger counts, the average tip amounts for trips that are not that long, below 5 miles, and I group this by the passenger counts, right? So this is basically asking for short trips, what's the average tipping people give with grouped by the number of people that were in the car, right? So if you have more people in the car, does the cab driver gets more money, less money? That's kind of what we want to discover. And we not only can read this directly from the data, from this data frame we created, and we do this by just naming it here. So the name of the data frame is df. We just do it from df like it was a table. But we can also output it to a data frame by executing the query and doing a .df. So we're outputting a data frame. And the reason we want to do this is because it turns out that Pandas actually is very tightly integrated with other libraries. So since I want to plot this and Pandas can already plot it directly, I thought it was just an easy way to go. So if we execute this, we'll see that it took 0.24 seconds for DuckDB to execute the query in the data frame, and output in the data frame. And the plotting, of course, was not timed, but here you can see how much tipping each taxi driver gets for the number of passengers. This is a bit weird. I think the data set's probably dirty. Or, I don't know, maybe ghosts are tipping taxi drivers really well. This is to be found yet. So I have the same query in Pandas. Not going to go into much detail about it. I'm more interested in the benchmarking and the same plotting, right? So as you guys can see, it's going. Oh yeah, 1.25 seconds. You can see it's exactly the same plot we had, but this is already 5, 6 times lower, right? So there's already a significant performance difference even in a OLAP machine. This is not a very powerful machine. If you guys do the same thing in your MacBooks, you'll feel possibly a higher difference. And here I have Spark, our 330 megabytes of binary pure performance. And I do the same. I read, actually not, because I tried to read on a data frame, but Spark ran out of memory, so that didn't work. But the Spark read from the Parquet file, so he has that thing, like I'm gonna give him some advantage over DuckDB, of course, for a little bit of fun. It does the same query. So I got a warning here about 5 minutes. Let's hope it finishes on time. Yeah, but yeah, I mean, we can talk about anything you guys want, actually. So you guys like sports? Oh my God, it's still going. Man, I should prepare jokes for this time or something, right? Like I can do a full monologue maybe. Oh, I hope it finishes. I mean, it's 330 megabytes, maybe that's it, huh? It's just, oh yeah, finished. So this takes like 3 seconds. Okay, that's pretty bad compared to, to 0.2 from DuckDB. And here you see, same chart. Here's a bonus, but I'm gonna skip this. But that was the idea, just to give you like a little tease about DuckDB. So a quick summary. DuckDB is an in-process database system. It's really focused on this type of fast data transfer, so interaction with other libraries, really trying to do zero copy whenever possible. No dedicated server hassle. Things just work. All the goodies from analytical database management system. So again, like all the years of research, we really tried to put it there as best as we could. It's really designed for analytical queries, so data analysis, data science, completely open source. And although DuckDB Labs, we are a company, we have clients, everything we do goes to the open source, or 99% of what we do goes to the open source. So basically, you guys are getting everything that's there, and it's completely free to use. Has binding for many languages, so here I showed Python, but honestly, whatever language you think we probably bind by today. It's tightly integrated with these analytical ecosystems, and this is my favorite one, SQL. That's it, guys. Thank you so much.